one thing that I've been doing in recent semesters as we've tried to take a lot of these general education courses like math and things like English and reading and so on, and really investigate what it means for these to be general education courses rather than, say, major specific courses. One thing I've been trying to do to incorporate something more along the lines of general education um, into these courses is do kind of like a quote of the day or an idea of the day that I think applies to the course, but also maybe a little more generally. Um, so we'll start with a quote of the day, kind of roughly each day. I might forget here and there to pop one at the beginning. Um, and then the plan for today is to just really quickly review attendance. We had a couple folks who weren't here last time, and just wanted to make sure that everybody who is on the roster for the course knows that they're in the course and that there weren't any registration issues or anything like that. Um, and then we'll start into the material for chapter one, just discussing some applications of stats, having a conversation about um, the utility of statistics and so on, and starting the chapter one PowerPoint. Note that the first assignment, as I mentioned last week in class, was due yesterday on Sunday. That was just the kind of assignment. It was all multiple choice, I think, or almost all multiple choice, and it was almost all from section 1.1. You could just leaf through that section, or maybe look in the index for some of the material that wasn't from 1.1. But I think it was pretty straightforward, mainly just to get everybody logged onto my stat lab, kind of understanding where the assignments are located, all of that. But the first kind of actual assignments are now posted 1-1 through 1-3 with these due dates. And note that on these assignments, you'll have 5 attempts per problem instead of the unlimited for that first assignment. Okay, so the quote of the day is from P.T. Barnum, the famous like circus guy. And it's a bit of a long quote, but basically the first sentence here is the one that I want to kind of focus on, that true economy consists in always making the income exceed the outgo. We always want to have a margin in favor of the income. And I think here he's kind of talking economically, but I think this is a general life lesson that in life, when we can build in margin, that's very important. That's very beneficial. So when you're looking out forward to the exams, or to maybe a class project in another class, or a big paper or something like that, if you start a little bit earlier, and if you start studying or prepping, say 2 weeks or 3 weeks ahead of time, if something crazy happens, if your car breaks down or something, or there's a power outage or something like that, this thing that kind of could be a catastrophe becomes an inconvenience. You have enough margin built in that you can handle these things that come your way. If you're on razor thin margins, if you're like, okay, it's going to take me, I think 6 hours to research and write this paper and do a decent job of it, and you start that 6 hours before it's due, you have zero margin. If something happens, if there's a power outage, if your car breaks down, if you get called into work, whatever, then there's zero margin, and that inconvenience becomes a catastrophe. So I think this is something that I see in my life. Like, if I'm driving somewhere and I leave myself just enough time to get there, I'm much more frustrated with other drivers. I'm much more annoyed if I hit a red light. If I leave myself 5 extra minutes, maybe that means I have to wake up a little early, or turn off Facebook a few minutes early or something. Then things tend to run more smoothly. So as a general rule, I think that building in margin into your life where you can is important. Of course, that's nice to be able to do financially, and that's great when you can do it. Not everybody's able to do that financially, but I think we're much more able to do that, for some of these other things with life, starting, the homework a little earlier, not waiting till Sunday night to start homework that's due on Sunday, starting studying for exam, and so on. Okay, so I want to really quickly review attendance, and I'm just going to call the couple of people that were not here last time and are also not on my stat lab. So if I call your name, if you can either speak up or type something in chat. And my chat just disappeared. I minimized it, but no, I can't seem to maximize it again. Zoom drives me crazy sometimes. There we go. Okay, so is Brittany Brown in class? Brittany? Okay. Charles Karelitz? Charles here?
Yeah, I'm here.
Okay. And Gregory Smith. Is Gregory Smith here? Gregory. Okay, so last call for Brittany Brown or Gregory Smith. All right, and everybody else I either saw in my stat lab on the roster or they were here last time on day one. If you haven't signed up for my stat lab, which a few people who were here last week still haven't, make sure to get yourself signed up for that. I think there were 4 or 5 folks who still haven't signed up for that. So the first assignment is already passed. And again, the next couple assignments are on there. There is the 2-week free trial. So even if you don't have an access code or whatever yet, you can get yourself signed on, get yourself started up while you get any of that worked out. Okay, so I would like to start with discussing a definition of statistics. The book gives kind of this, I don't know, like very wordy and not very informative, I don't think, definition of statistics. But I want to just kind of think through this. Does anybody have an idea of, what does statistics mean? Like when you hear the word statistics, if you had to give a definition, if you had to explain to somebody in one sentence when they say, wait, you use this word statistics, what does it mean? What might be the sentence that you would say to somebody? Any thoughts on that? And you can just speak up if you have an idea.
Excuse me.
Yeah.
I'm actually reaching out because the link that you sent, which one are we supposed to use? Because I thought last week you said there's 2 links in this in the course material, and I clicked on the one for Monday, and I've been sitting waiting on a meeting, like an entry, and then I went back out and went to the other link you sent.
Do you mean which link are you supposed to use for the class meeting?
Yeah, because you sent 2, but
Um,
there's 3.
but you're in the class meeting now, right? I
Right,
mean,
but
yeah.
I'm just
So you
trying
would
to
use
clarify
this link.
because
Yeah.
and that's for Monday and Wednesday.
Correct. So you're saying the announcement I sent on Blackboard last
If you
week
go
is
to
that?
So if you go into the section that says Zoom, it says Zoom links. You have
Mhm.
2 in there for, whatever days. There's one in there that says like to get into the class, click this link, but then you have a set of 2 right below it.
For office hours?
Okay, so those are for office hours, not for the actual class.
Yep. Yeah, where it
Okay,
says
just
my
I just
office
wanted to
hours will
clarify.
be join the Zoom meeting. Yeah.
Okay, thank you.
Okay, so as I was saying, the definition of statistics. So if you had to give somebody a 1-sentence explanation of what this word statistics means, if you used it in a sentence and they said, what do you mean by that? Are there any thoughts on either what sentence you would tell somebody, what explanation you would give, or at least a component of it? What would be a part of that explanation?
Professor, yeah, if I would, like, my definition of studies is like analysis or collection of data over the past period, that we can use for the future plans or like for the future analysis or predictions. I would define it as like this. Yeah.
Yeah, I think that's a really good explanation. So analysis or collection of data to use for prediction or planning for the future. Yeah, I think that would be an excellent concise explanation of what statistics is. Any other thoughts? Anybody have a different perspective?
What, kind of like the study of ratios?
Yeah, in a sense, kind of the study of ratios. That statement might be just a little bit broader than statistics in general, because we could talk about ratios like, miles per hour or something like that. But yeah, I think this gets at the important idea of something along the lines of like a percent chance of something occurring, or maybe what we would call a probability.
Probability, yeah, I was gonna say that.
Yeah, so I think most people, at least in this context, would think of probability as kind of a sub-discipline of statistics, although mathematicians probably would think of it kind of the other way around. They think of probability as being the mathematical structure and statistics kind of deriving from there. But I think in terms of application, we might think of probability as being kind of part of statistics rather than the other way around. So it might depend a little bit on perspective. But yeah, some ratios are very important ideas in probability. And what I would kind of say with statistics is, I think statistics is kind of the process of converting nearly useless raw data, and we'll talk in just a second about what we mean by raw data, into a more usable form. My handwriting is just not very good today. I think I'm trying to write a little too fast, and maybe haven't written on this notepad for a month and a half, and need to get it back in the muscle memory. So converting nearly useless raw data into a more usable form. I think this first definition is excellent. I think the second comment brings up part of this as well. But what do we mean by raw data? So as mentioned in the kind of first definition is, well, collection of data is quite important to statistics. I think we all kind of intuitively understand that this is something like a data science, in a manner of speaking, that we're trying to go out into the world and empirically study it, that we're trying to collect some kind of data from the world, look at that data and understand something more about the world, at least roughly speaking. So what is raw data? It's data in its initial form. And one of the examples that I typically use for raw data, just because it's kind of easy to understand and think about, is you think about, say, the S&P 500, right? If you see the news stories or whatever, they talk about the market's up or the market's down. Well, that usually refers to something like the S&P 500 or maybe the Dow Jones. But the S&P 500 is basically just kind of like the overall value of the stock market kind of as a whole. That's roughly speaking what it kind of represents. And maybe I could look at, say, daily S&P 500 values at, say, the close of business on each day for the last 10 years. So if I have, say, 10 years of daily S&P data, there's roughly 250 business days per year. This is a list of about 2,500 numbers. If I handed you a sheet of paper or several sheets of paper with just columns and columns of numbers, 2,500 numbers, I mean, that's good data. Like, this is the daily close for the S&P for each of the last 10, each business day of the last 10 years. But that's not super helpful to you, right? We can't really understand much about what's happened the last 10 years with just 2,500 numbers sitting in front of us. We can't really make inferences. We can't really make guesses about what we think might happen next week or next month or next year on that basis, just with this big list of numbers. I would really like to take this data and convert it into a form that is a bit more usable, is a bit more useful for me as a human. And there are a couple ways that I could go about that. And kind of the way that I like to kind of think about things in the hierarchy of say knowledge or understanding or something like that of the world is at the very bottom we have data, or just raw data. And this is kind of, when we go out in the world, we collect some information, right? Maybe I should be a little careful with my nomenclature now, because I'm going to use information a little bit differently later on, but I collect data. I collect, measure the heights of certain people, or I investigate the S&P 500's closing prices, or whatever it may be. If I do some crunching on that data, maybe I take those 2,500 numbers and I ask, okay, what is the average annual return of the market? I can say, okay, kind of on average over these last 10 years, if I, bought a big chunk of the market at one day, I waited a year, and then I sold it, how much money on average would I make or lose kind of across that whole 10 years? Well, that tells me something about what has happened, right? It takes these 2,500 numbers, crunches them down to one number, and I can look at that number and I can much more easily understand that one number than the 2,500. But that comes at the cost of losing a lot of that data, right? I have one number, so it's easy to understand, but on the other hand, it's less broad. It's just one number. It doesn't tell me all of the nuances of some years were up, some years were down, some years were flat. So I lose some nuance, but I gain some understanding. So maybe I could move up a level of, say, understanding of the phenomena in the world that I'm interested in studying. And I can move to something like maybe information. Maybe this is like, an average annual rate of return, or maybe like an average height of people in Pittsburgh, or something like that. I have my raw data that might be hundreds or thousands or millions of just numbers. I do some crunching on that to make it a little bit more usable. I think that's a good first step. And then we might try to jump a step further. So this first step is kind of internal to the data. We're taking a big data set, crunching it down to make it easier for us to understand or to model what's going on in the world. And then once we feel like we have a bit of an understanding, we might be able to develop a model. We might be able to develop to do some analysis and particularly predict or plan what we think will happen either in the future or maybe external to the data. So I might try to develop something I might call knowledge. I might try to develop a rule that I think, maybe I roll a ball down a slope a whole bunch of different times in a physics lab, and I measure the slope angles and the times that it takes the ball to roll a certain distance and so on. And maybe I try to develop what I think might be a physical law on that basis. So maybe I say, okay, I think I've rediscovered F equals ma on the basis of this experiment of all of this data. So that's kind of a more general rule that I think is followed by whatever thing I'm studying. Or maybe I see, oh, the average annual return over the last 10 years was, let's say, 10% per year. Maybe I think, okay, if I'm going to invest my money for 10 more years into the future, maybe I would expect to get something in the ballpark of 10% per year return. So maybe that's knowledge. Maybe I build a model off of this information and I gain even a deeper understanding of the thing I'm studying. And then I think the kind of top of the ladder here, and by the way, this isn't like in the textbook, this is just kind of the way that I sort this out in my head. I don't even know if everybody uses these 4 words the same way that I do, but this is the way that I use them. And the top of the hierarchy here is wisdom. So in other words, if I have the knowledge that, if I take all of my money and put it in the S&P 500, I think I'll get 10% per year. Wisdom says, well, should I do that, right? Knowledge might help me to achieve the goals that I choose to want to achieve. Wisdom is the thing that says, well, what goals should I set for myself? What things should I want to achieve? Should I just want to be rich, or should I say, no, I'm not going to give my niece or nephew any birthday presents because that'll take away from my money and I could put that money in the S&P and, get more money later on. Well, these are questions of wisdom. In statistics, we're trying to focus on these bottom three, we're trying to convert data into information and information into knowledge, I would argue. And we leave wisdom to either philosophy or religion, depending on, or both, depending on your kind of perspective. So we leave that to kind of the philosophers, the pastors, to say, okay, what are good goals to set? But once we set goals, quite often when we set goals, we say like, I want to have a good retirement, or, you know, I want to know, maybe average height isn't, people in Pittsburgh isn't a good one for this, but let's say we were looking at, say, average blood pressure of people in Pittsburgh. And I want to say, I want to know if a certain, you know, medical intervention will lower people's blood pressure on average. You know, maybe my goal is to make people healthier, and will this intervention actually make people healthier, or won't it do anything? So once I kind of set a goal, quite often, not for every goal, you know, statistics and math doesn't answer all of the world's questions, doesn't solve all the world's problems, but often once I set a goal, I can go into the world, I can collect data related to that goal, crunch the data, get a little bit more understanding of how the world works in relation to that goal, develop a model, a more formal model, or maybe just kind of an intuitive model of how the world works, and then make actionable plans for achieving my goals that maybe have a better chance of success than if I hadn't gone through this empirical process. So I would argue that really, you know, stats is trying to move up the hierarchical ladder of understanding our world in these bottom three tiers, and then we leave it to kind of the, you know, the other folks in the other disciplines to decide what goals we should be aiming for. What should our, you know, kind of long-term perspective be? You know, should we head to Kansas or Maine? And then, you know, what stats can answer for us maybe is like, what roads should we take to get there once we decide what destination we want to go to. Okay. So as far as statistics, if somebody said, you know, oh, I, you know, work in the field of statistics or whatever, is there something that brings to mind for you? Is there an application where you see a lot of statistics used, or is there an application in your field of study or your field of interest or the career you're looking to go into where you think statistics might be used? Any thoughts on some applications?
Like in the medical field, like medical studies to, I don't know, for like cancer, for example, like to see if medications work.
Yeah, exactly. Medical field. So clinical trials, evaluating, say, the efficacy of a medication. So we have, you know, whatever it may be, a TKD inhibitor or something, and we have a new one that comes out, or maybe we know that it works in this cancer and we're curious if it works in a different kind of cancer. Maybe we know it seems to treat lung cancer, certain types of lung cancer well. Does it treat kind of related, seemingly related colon cancer as well? Maybe we run a clinical trial. We find some people with colon cancer, we give them the drug, we see if they kind of do better than if they had not gotten that drug. Of course, there's all kinds of ethical concerns and all that you would have to hash out first with all of that. But, you know, just at a high level overview, yeah, something like efficacy or something like safety, right? Is this drug, are the side effects so terrible people can't tolerate it? Is there another drug that's just as effective but has lower side effects or a greater margin of safety? Yeah, so definitely medical field. I mean, if you open up any medical journal, any JM, the British Journal of Medicine, the Lancet, the JAMA, any of the, you know, you open them up and pretty much every article that you read is going to have a slew of statistics. They're going to have confidence intervals and hypothesis tests and p-values and all of these kind of things, as well as descriptive statistics like charts and graphs and, you know, histograms, all these kind of things. So absolutely, the medical field, one of the biggest users of statistics. Any other fields?
Professor, I would say
this.
information. What's that? I would say information technology field, because there are a lot of like data generated in IT, you know.
Yeah, definitely in the IT field. And yeah, IT is, you know, kind of a pretty huge field, but we could think in terms of something like, let's say, call centers. So like our help center, I mean, they log all of the calls. And if all of a sudden they're getting a whole bunch of questions about, you know, this particular whatever, you know, CCAC Central or something like that, maybe they can actually take that data that they collect and they can have some automated process that says, hey, we've gotten a lot more questions about this subtopic than we typically get. Let's send that to somebody. That person might look at that and say, oh, that's unusual, right? They might take that raw data. It might be crunched in the background, sent to somebody. They might say, hey, that's unusual for us to get this many questions. They may be investigated. They maybe suspect that maybe there's an underlying, a fundamental problem with this system. Maybe it's the server's offline or something like that. And that's more knowledge about the world that they can act on and investigate the problem further, fix the problem. Yeah, anything like that. I mean, related to that is artificial intelligence or machine learning. Huge fields these days, obviously. And this really is like, I call it kind of like the sledgehammer method. You know, we just collect a ton of data, and we kind of over the last 20 years or so, we as a society have been collecting tons and tons and tons of data. And we're really starting to get to the point where we can use that data really well. There are types of predicting the future that look like, say, F equals ma from physics, right? That kind of a model where we say we collect experimental data and we try to develop some kind of really nice, clean mathematical model to make a prediction. We understand what each of the components of the model is. We kind of understand what mass is, what acceleration is, what force is. We now understand how these components relate. We can then build on that model and say, okay, how would F equals ma look in special relativity? How would F equals ma look in quantum mechanics or for a photon or something like that? And I can make guesses based on that model because I have an intuitive understanding from the model. That takes an awful lot of time and effort and really genius to come up with those kind of models, right? Not everybody's Isaac Newton. If I just need an answer, I need the answer tomorrow, and I have a ton of data, and I don't have the time or the resources to try to develop one of these really pretty mathematical models, or maybe the system I'm studying is sufficiently complex that I don't think that there's going to be a nice mathematical model. I think if I could come up with a model, it's going to be extremely complex. Well, maybe I could basically just say, hey, I have a lot of data. I have a lot of computing power these days. I probably have more computing power on my cell phone than we had in, you know, a whole computer, a normal home computer, you know, 15 years ago or something. I have a lot of computing power, I have a lot of data. Can I just merge those two together? Can I just like whack the problem with a sledgehammer and use this ton of data, ton of computing power to try to get me an answer quickly? Now, the benefit of that is I can get the answer really quick. I can say, you know, Amazon can say, what products should I recommend to this person that they're likely to be able to use in, you know, in the near future that they're going to want to buy. Now, it makes it harder to build off of those models. If we have a really good AI model that says, here, you know, here's our recommender system, you know, there's whatever 10,000 nodes or something, and when these nodes, you know, or these values, it says to recommend this product instead of that one to this certain person. Well, I don't really, I can't say, okay, can I build on top of that model? So that's kind of a shortcoming of this AI machine learning. We're getting answers quickly, but our models aren't as intuitive. We can't build as much understanding off of them. It's in a sense a different kind of knowledge. We kind of know something about the world, but only empirically and not really more fundamentally. So at least from my perspective, which I'm certainly not an expert in AI or machine learning, but from my perspective, that's the trade-off. You get very quick answers, reliable answers with, relatively speaking, low cost because we've already collected so much data and computing power is cheap these days. But that's at the expense of really the more fundamental understanding of the process. And sometimes you want one, sometimes you want the other. So it's not that one or the other is bad, it's just a question of which would best serve your goals. Yeah, somebody in chat said, so in business, so sales, so how well your product is selling, you bring a new product to market. What do your sales look like? What does the rate of change of the sales look like? If you go from month to month to month, does your marketing seem to be working? Are your sales increasing at the rate that you would expect them to increase over time? Yeah, so another person in chat, NASA. So yeah, data scientists that work for NASA. We're actually, so I'm on the sabbatical committee for our faculty. And so our faculty every 6 years can apply for a sabbatical, and they can say, I want to take a semester off of teaching to do this special project. So they kind of get paid. They don't have to teach any classes, but instead of that, they do some kind of special project. It might be research, it might be working on a degree, something like that. And this is all, don't latch too much onto this, but we have a couple of telescopes at some different campuses. And one of our faculty members has applied for a sabbatical to really kind of beef up the telescope program at one of the campuses. And he wants to kind of do some like star parties and invite people from all around, from the general population of the area, not just our students, to come and kind of look at these resources. But one of the important things involved with all of these telescopes is there's a lot of data crunching. There's a lot of computing that goes on. There's a lot of programming that goes on to say, okay, the telescope is just kind of this thing that's getting photons or whatever hitting it. Like, what does that actually mean, right? Or when you like look at a picture in quotes of a black hole, it's not like somebody flew out and flew by the black hole and snapped a picture with a Canon DSLR or something. There's a lot of data crunching that goes on to make these representations that are somewhat like a visual representation of a black hole or a star or something like that. A lot of the data that's coming in is not in the visible spectrum. So how do you make it something that we can see and appreciate? So exactly, yeah. NASA, there's tons of data crunching with that. We'll see an example later on with the NASA's Kepler project, looking for planets that are kind of like similar to Earth, where life forms kind of like us might be able to live. And that also uses a lot of data crunching to try to find these planets. Yeah, definitely politics. Oh. If you ever, follow the political races as the election is happening, like on election night, they have the map of the US or whatever, and it's like, oh, we can call these states for this person and those states for that person at like, 7 p.m. or 8 p.m. or something. It's like, but wait, you don't have all of the votes in. How did you make that call? And of course, the call is not official, but there's some statistician somewhere saying, okay, the margin is sufficient between the two, that is it really actually likely that that's going to flip-flop, as if we have 90% of the votes in and one person's winning 53 to 47% at this point, do we really think they're going to close that gap and switch with this last 10% of the votes? Maybe probably not. If it was 80% of the votes in and 49 to 51, that might be too close to call right now. We might have to wait a little while. So yeah, all of these things with politics and elections and things like that, even earlier in the day, like exit polls, when people just come out of the poll and you ask them like, hey, who'd you vote for? And, they collect that data and see how things are going. I think it's a little bit funny or amusing to think that like you'll have the actual answer in like less than 24 hours, but we're just like so impatient that we'd rather have, a very unreliable answer at like 3 p.m. than wait for, 8 a.m. the next day and just look it up and see who actually won. It's a little amusing to think of that, but and also in politics, things like, kind of the other side, the person's elected, they're in the government, and they say, okay, well, we have this idea on the table, maybe we want to pass this law, or maybe we don't. We go out to our citizens and we say, hey, do you want this law or not? And the citizens are going to respond. And, typically they're not all going to respond, of course. So we have 5% of our citizens write in and say yes or no, I want or don't want this law. And on the basis of that small sample, we're trying to make an educated guess as to whether the folks in the area want this law or not. At least maybe that's how it should work. I'm not so sure if it does work that way, but I think in an ideal case, it would work something like that. Yep, pharmaceuticals, that kind of, that ties back into the medical field, the pharmaceutical field, looking for new treatments and evaluating whether those treatments, those drugs are both effective and safe. So taking them through a clinical trial. So definitely. Yeah, so as far as like tools or techniques in the field, so some things like SQL, the structured query language, it's a programming language. Some would argue it's not a programming language, but SQL is Turing complete, so you can call it a programming language. And if somebody doesn't like it being called a programming language, I guess they don't have to call it that. But SQL is a programming language that you can use to take big databases and kind of comb through the databases and get just the data that you want. So you can write a query that says, like we use this all the time when we're planning the courses from semester to semester. So like, how many sections of MAT165 should we offer next semester and what modalities? Well, we might look back through, say, the previous 3 or 4 terms. We might pull all of the stats courses and look at, what the enrollment numbers looked like for which modalities, and try to project into the future and decide, on the basis of that query, on the basis of that data and information, what do we think we should offer, say, next semester? And then Excel, yeah, definitely. So just another tool for kind of number crunching, for also displaying some data, for making charts and things to make a visual representation of this big bunch of numbers that we can't really interpret very well. But if we have a picture, a lot of times that's much easier to interpret. Yeah, so manufacturing and engineering. So a great example is in manufacturing and quality control. So if we're manufacturing, whatever it may be, let's say cars, right? And we need to have pistons where the cylinders and the pistons and the piston rings all kind of fit together just right. What are the tolerances, right? Of course, if we want a piston that's whatever 4 inches across, it's never going to be exactly 4 inches across. How much of a tolerance am I okay with? And if I produce these pistons and at the end of the line I measure them, at what point outside of that tolerance, maybe one of them just gets wonky and I just throw it out and I keep the line running. But if too many of them are wonky, I'm going to say, okay, I think maybe my machine is broken. It needs calibrated. At what point would I make that call? Is it like if 1 out of 10 pistons is wonky, I make the call to recalibrate the machine? Do I care how wonky it is? So absolutely, that in manufacturing, that's a huge question, is quality assurance, quality control, how to make sure that the product that we're producing and that we're shipping to customers is actually qualitatively what we're saying that it is. And in engineering too, of course, all kinds of things, strength of materials, soil analysis, all of that kind of stuff uses statistics. Yeah, sampling would be a kind of tool or technique over here. And the basic idea of a sample versus a population is, and we're touching on some of the chapter 1 material as we're talking through this as well. So we're touching on some of the stuff from the slideshow as we're going through this introduction. The basic idea of a sample versus a population is that, let's say that I want to know something about all of the people in Pittsburgh. And let's just suppose that we've gone through the effort to define exactly what I mean by all the people in Pittsburgh, whether I mean everybody located in some geographic region right now, or everybody who lives in Pittsburgh or whatever. But let's say that we know who exactly we're talking about as the population, as the group of folks we want to say something about. And maybe we want to say something like the average height of people in Pittsburgh is blank. Well, the problem is that if there's 1 million people or something in, say, Pittsburgh, the greater Pittsburgh area, well, it's going to take me a ton of time and effort and resources to go around and measure all of these people's heights. And probably most of them aren't going to let me measure their heights anyway. So I want to say something about everybody in Pittsburgh, but I can't reasonably do it. So what could I do? Well, maybe I could, instead of trying to get all the 1 million people's heights and compute their average, maybe instead I could say, well, what if I take a sample of 1,000 people? What if I randomly choose 1,000 people from the population? And maybe I do have the time and the resources to measure these 1,000 people's heights. And if I compute the average of the sample of 1,000 people, maybe I kind of hope, or I feel that it ought to be true, that that average should probably be close to the average height of all the 1 million people. And we'll talk extensively later in chapter 7 and 8 about why we think that ought to be true. What's the mathematical underpinning that says that that's a reasonable thing to do? It's not just because we have a gut feeling that that seems like a good thing to do. There is definite mathematical support for doing something like that. And that's really what all of chapter 7 and 8 is about. But absolutely. So it's the typical situation when you're doing any kind of analyzing data is you want to make a statement about a population, but the population is too big for you to realistically evaluate the whole population. So you take a sample of the population, you randomly choose some folks from the population, you treat them as kind of like a small microcosm of the whole population. You do your analysis on the sample, and then you hope that you can extrapolate, that you can make inferences about the population, that you can extrapolate the knowledge gained from the sample and say something about the population. And you do the same thing, this might seem like a very hand-wavy thing or a very questionable thing, but you do the same thing in physics, right? You go to a physics lab and you roll the ball down the slope and you do it a bunch of times and you come up with F equals ma. Well, you didn't do that experiment in Australia too, just to make sure it works the same way, or in Antarctica to make sure it works the same way there. You did it in one location at one point in the whatever gravitational field or whatever. You only did it on Earth. You didn't do it on Mars. You didn't use a billion different ramps of all kinds of different angles. You maybe use 3 ramps with 3 different angles or something. So we kind of always are doing something like this. Just sometimes it's, I think, a little more obvious than other times. Are there any other thoughts?
Is there a difference between sampling and surveying, or is that just like interchangeable?
Yeah, I would say that surveying is a subtype of sampling. Yeah, that's a good
Okay.
question. So kind of like a survey might be something like, calling people at home and asking them, what TV shows do you watch or whatever, what is it, like Nielsen ratings or something like that. I think they used to do that. I don't know if they do anymore. Today with everything streaming, they might just kind of, see who's downloading what or whatever. So there are things like that are kind of more survey based, or like Gallup polls, or like election surveys, where you go out and you kind of ask people for the information. There are also things like, if you're interested in medical information, UPMC has tons and tons of patient charts that are all electronic now. Provided that you do this ethically and everything, you can kind of comb through all of these charts. You can write a program that says, pull all of the people that have heart disease or that have high blood pressure or something, and we want to know whether maybe these two correlate with one another, whether when you see that a person has, high blood pressure, they tend to also have heart disease, maybe at a higher rate than we would expect at baseline, something like that. So that would still be maybe sampling, because we're trying to say something about like people in general, whether it's all of Pittsburgh or like all of the country or all of the world. We're probably trying to model people in general, but we're using the folks that are in our electronic medical record. So we're using a sample, but I wouldn't exactly call that a survey though, because we're kind of doing like data mining there. Yeah.
Okay,
So
thank you.
Yeah, that's a really good question. Yeah, surveying would be kind of a type of sampling. Any other thoughts on either tools or techniques or applications to a certain field? So one that I'm actually surprised nobody mentioned is sports, right? All of these pieces of data about sports, and baseball and football and all that, they're always throwing around like what's the average pass yards, or what's the quarterback rating, or how many points per game do they allow, or in baseball, how many runs batted in for this team, or what's this person's hit percentage, are they 300, are they 350, 30%, 35% of the times that they're at bat they get on base, things like that. So tons and tons of data in sports, almost to the point where it kind of sometimes becomes like, people like joke about it, it almost becomes a meme where it's like, oh, this is the first time the left-handed pitcher with the initials whatever JY has pitched on a sunny day, that at and thrown a pitch that's over 99 miles an hour or something. It's like they start adding all of these qualifications, and it's like, well, at some point, you can add enough qualifications that it's always the first time that something has happened. But yeah, so sports, see from my list if there's anything kind of interesting. Well, weather, we've seen some crazy weather recently. What's the coldest day in history, or whatever, coldest recorded day in January, in Pittsburgh, or whatever it may be, or talking about, there's a 30% chance of rain tomorrow. What does that even mean? We'll talk about that a little bit in a couple chapters. Yeah, something that's come up recently in the medical field is things like vaccine safety or efficacy. And this kind of points to the idea that statistics, it's in a sense, purely logical science. If we say, here's a data set, compute the average, it is what it is. But there's also a lot of, typically the questions we're trying to answer important questions about the world. So there's also a lot of, emotion, and there's a lot of other things that play into some of the background here. There might be things that play into, why did you choose this sample over that one, or this population over that one, or this data set over that one to analyze or to present or to build your models off of. So there are things like that play into statistics. We might look at statistics in a sense as a purely mathematical field, but really there are a lot of choices that go on in the background. What data set do I choose? How do I choose that data set? How do I choose the population that I'm talking about? And that really came to a head a lot with the COVID vaccine and all of that. And there were people very divided into camps. And at some point, if you lose credibility, and on either side, if you lose credibility, people just aren't going to trust your data. And that's, a little bit about those kind of two books that I mentioned the first day of class, How to Lie with Statistics and Statistics You Can't Trust. It talks a little bit about that, that when data is misrepresented, or when somebody feels it's being misrepresented, it doesn't much matter what the numbers say, because they're just not going to trust the numbers. There are enough decisions made in any statistical model that you need to have a high degree of credibility for the numbers you present to be believed. And then some tools also, things like graphs. So like your good old, histogram, bar chart kind of thing. A lot of times these can take a lot of numbers. We could also have, say, a line graph like the S&P 500. And if I look at a graph like that, that might be representing, say, 2,500 numbers. And I can look at this and say, okay, like overall an upward trend, there were a couple of dips, a couple of, bad years maybe, and maybe a couple of strong years. looking at a picture, I can tell that much more readily than, looking at, say, a list of 2,500 numbers. Yeah, there's a question, is there ever a sample taken of the samples themselves? So it's an interesting question. So there's this idea called bootstrapping. And we'll probably talk about it in chapter 7. It's one of the kind of optional topics in the course. We might get to it, we might not, but we typically do talk about it. And bootstrapping, you take a sample from the population. But again, what's the purpose of that sample? It's supposed to act like a microcosm of the population. It's supposed to be just like kind of basically a shrunk down version of the population as a whole. You can actually then, in a sense, kind of look at that sample as its own kind of population. And then you can sample off of that sample. You can resample, and provided you do it kind of the right way, that can actually be informative and helpful. So kind of a short answer is yes, in certain situations. But if we just did something like took a sample of size 1,000 people in Pittsburgh and measured their average heights, we probably wouldn't then like take a sample of size 100 from that 1,000 and like measure their average heights too and like report both of those averages or something. We probably just would stick with a bigger sample most of the time. Okay, so there's a question in chat about what about population, like where do people like living the most? Yeah, so actually one of the graphs that we'll see in chapter 2 is kind of a histogram of the percent change in population for each of the 50 states plus DC over a 10-year period. And we will see that there are some areas that you'll see like big population decrease in a year, and then the surrounding areas had pretty nice population increases that same year. So yeah, we can see things like that coming out in the data as well. Yep. Okay, so hopefully hopefully everybody in here has seen at least a couple of applications that they find interesting or that they find engaging, and hopefully we've gotten a little bit of an idea of what tools we'll be using throughout the course to try to crunch numbers, to try to make inferences, to try to build models, and so on. So let me now switch gears. Let me stop my screen share, and oh, I didn't want to close that, wanted to minimize it. All right, there we go. Okay, I'm popping a oh, this always defaults to direct message when somebody sends me a direct message. There we go. I'm popping a PowerPoint into the chat. The PowerPoint is also on Blackboard under supplemental material, PowerPoint presentations. So you can find it there later. But I just posted a PowerPoint presentation in the chat, and that's what we're going to be going through now. So let me get that open, switch my window over. And I am going to close my chat window for now because otherwise it's kind of tough to get everything on one screen. Can I? Sorry, give me a sec here. There we go. Just getting everything lined up here. I love Zoom, but the transitions can sometimes take a few seconds to get worked out. Okay. All right, so we're going to start this this PowerPoint on chapter 1. We won't finish it today. We'll probably just about finish it next time. We might bleed over into the next the next day, we might talk about a couple last little topics, but we should get through most of it this week. And the quote, I know we already did a quote of the day, but kind of the quote for chapter 1, and really kind of the quote for all of the course, I'll probably say it, 30 times throughout the course, is from statistician George Box. And this quote from him, essentially, all models are wrong, but some are useful. And that's really this idea of trying to move from data to information and knowledge. When we build models, when we try to get knowledge about the world and say things about the world that are sufficiently complex to be helpful, we're probably going to be wrong, right? Our model is not going to be perfect. F equals ma is not a perfect model. It breaks down at relativistic speeds. It breaks down in some sense in quantum mechanics. But it's very, very useful, right? There are a lot of domains, a lot of things that we care about, where having that model is much, much better, where we can plan much, much better and predict much, much better with it than without it. And I think that's a really important thing to understand with statistics, and really with kind of anything in science, is we're dealing with models, we're trying to understand the world better, but at no point are we saying that we have a perfect understanding of the world, or that somebody else's interpretation of the world is just flat out wrong and that ours is 100% right. Especially in statistics, there's just always this little bit of wiggle room. I'm 99% certain that my answer is between these two numbers, but it's not that I'm 100% certain my answer is exactly this number. And we've already talked a little bit about the definition. The book, again, gives this like paragraph long definition, but I think, that should not be hyphenated. Nearly useless should have a space, not a hyphen there. So typo already on the second slide, but basically statistics converts nearly useless raw data into a more usable form, into usable information, or maybe from there we might even move into knowledge. We might be able to make inferences. So some important concepts and ideas in the course: the idea of a variable. Just like in Math 108 or something, a variable is kind of a thing that can take on different values, and data are the values the variables can assume, or that the variables do assume, depending on just how you want to phrase that or how you want to think about it. So for example, a variable might be something like the number you get on the roll of a 6-sided die. And anytime we talk about rolling a die or rolling dice, we're always, unless otherwise stated, presuming that it's a fair 6-sided die. So numbers 1, 2, 3, 4, 5, 6 can come up, and they're all equally likely. So that might be a variable, right? I could say like x equals the number that I get on a single roll of a 6-sided die. X could be 1, 2, 3, 4, 5, 6. Or if I take a specific die and I roll it, 20 times, I have 20 actual instances of what such a roll was in each of those 20 experiments. So that would be the data. So if I have, if I roll it 20 times and I get, 1, 2, 6, 6, 4, 5, and so on, 3, 2, 6, if I have, say, 20 of these would represent my data. These would represent a data set for these 20 rolls. Random variables are variables whose values are determined by chance. We'll talk a little more about randomness in chapter 4. But for right now, this idea of what does it mean for something to be random is really a deep question. It's really a difficult question to answer. But there's kind of two ways to think about it. One is that there's some like fundamental randomness in the world, that like rolling this die, there's like, it's just a complete toss up 1 through 6. We have no idea what it would be, and there's no way to know what it would be. And there are some fields that are emerging that suggest that maybe at some very fundamental level that kind of a thing is true. When we talk about randomness or something that's determined by chance, we're really talking about a chaotic system. So we're always going to kind of take the point of view by default that if we had enough data and enough computational power and enough understanding of the world, when that die leaves the person's hand, we could predict whether it's going to come up 1, 2, 3, 4, 5, 6. But in reality, we can't do that. We just don't have the ability to do that. Or maybe in another scenario, maybe we hypothetically could, but it would just require so much resources and so much effort that it's just not worth our time and hassle to do it. So randomness is a mathematical structure. It's an abstract structure that we overlay onto the problem, and we say, okay, instead of trying to talk about, for this die roll, when it was released from the person's hand, like what were all of the velocities and the velocities and the forces at play, what's all the air currents and what's it going to bounce off of and how's it going to interact with all the things it bounces off of. Very complex thing to model. Instead of trying to do that, we're just going to say, okay, when it leaves their hand, we're just going to assume that it comes up 1, 2, 3, 4, 5, 6, equally likely, but we have no way of knowing. That's our model. Again, maybe in a sense our model is wrong, but this is probably a much more useful model than to try to do all of the crazy physics stuff and try to figure out what that die is going to come up before it actually lands. And what we mean by a chaotic system is that it's not easy for me to predict when it leaves their hand, whether it's going to come up 1, 2, 3, 4, 5, 6. And also a small change to the input can yield a large change in outputs, right? A 1 can change to a 6 very easily on a die roll. It's not like if I think it's a 1, it's probably going to be a 1 or 2, maybe a 3. It's like, I don't know, if I think it's a 1, it could very easily be a 6, right? It could easily be at the other end of the spectrum. So that's kind of what we mean by randomness here. This is a mathematical structure that we overlay onto the world to help us to understand and interpret it and to make predictions. We're not making an argument that this is fundamentally actually how the world works. A collection of data values forms a data set. So this that I have kind of in brackets here might be a data set representing 20 rolls of this 6-sided die. There are 2 main areas of stats, descriptive and inferential stats. And remember when we talked kind of up here, we said we start out with some raw data, but typically that's not very useful to us. It's not very easy for us to really say anything about the phenomenon we're studying on the basis of, 100 or 1,000 or 10,000 just numbers on a piece of paper. So descriptive stats tries to take that data set, that collection of a bunch of numbers, and describe some facet of that number. Maybe I take an average of those numbers and I give you one number that's the average instead of 10,000 numbers that's the raw data. You can understand the average much better than you can understand a list of 10,000 numbers. You can glean meaning from that, but that's at the cost of nuance, right? That average doesn't completely capture everything that was in those 10,000 numbers. Maybe I could make a graph. I could make a histogram of all of my stats students over the last 10 years. What were their final grades in the course? This many got A's, this many got B's, and so on. But I don't know which person got an A versus which person got a B, right? When I go to that histogram, it's helpful for me to look at that graph. It's easier for me to interpret, but I lose a little bit of nuance. So that's the idea of descriptive statistics. It's kind of like crunching data down. It's like you have this much stuff to work with, and you're crunching it down to less stuff that's easier to understand. Inferential stats kind of goes the other way. We have a data set and we build a model. We want to extrapolate from that data set. We want to kind of expand our view. We want to say, okay, I understand what happened the last 10 years in the market. Now I want to predict what will happen the next 10 years. I want to say something about 2,500 additional data points, what I think will happen there based on the 2,500 that I have. So I want to build a model that says something about 5,000 data points. I'm going outside of the data that I have. I'm extrapolating to try to make predictions, right? To try to predict the future, or maybe it's not even so much the future as if I'm in the pharmaceutical field, maybe I run my clinical trial and I see that, at 10 milligrams of dosage, the medication doesn't seem to be effective, but there aren't many side effects. At 20 milligrams of dosage, the medication is effective, but the side effects are pretty terrible. What do I think is going to happen at 15 milligrams? Can I make an estimate? I didn't actually run the trial with 15 milligrams, but can I make an estimate and try to decide whether it's worth spending all of the money to run another trial at 15 milligrams to see if we can get efficacy with safety and get a good combination of the two, safety or tolerability, whatever you want to call it. So those would be inferences. Descriptive stats, we're kind of just saying, okay, I have this data set. This is what I have right now. This is kind of my known about the world. I went out and collected it, but it's hard to understand. Can I crunch these data to make it easier for me to understand? And inferential is saying, this is my known about the world, this data set. Can I use this to make predictions that go outside of what I know definitively about the world from my data set? So inferential stats often uses probability, the chance of an event occurring. We discussed that up here. So this idea of studying ratios or probabilities is kind of a central idea that we'll be using throughout the course. So chapters 4, 5, and 6 are really studying probability, which is really kind of that mathematical structure. And then statistics is kind of where you try to take that mathematical structure and overlay it onto the real world and then answer real world questions using the mathematical structure we built up. So the kind of the general structure of the course is chapters 2 and 3. We're typically looking at descriptive statistics. We're taking data sets and trying to crunch them down and report an average or create a picture or something like that summarizes that data. Chapters 4, 5, and 6, we're building up that mathematical structure of probability theory. And then chapters 7 and 8, and kind of like 9 and 10 and 11 as well, but really focusing on 7 and 8, we're trying to take that probability structure that we've developed and overlay it on the real world and say, how can we actually answer real world questions using this mathematical structure? And also kind of using some descriptive statistics as well to help inform our models. Chapter 8 covers a topic called hypothesis testing. This is something that comes up quite a lot in the medical field. If you ever hear discussions of things like p-values or statistical significance, these are talking about hypothesis testing. So this is going to be near the end of the course, chapter 8. And it's a way to make decisions. It's a way to say, I kind of have to choose to believe one of two options. I have to choose to believe that the medication is effective or is not effective. How can I make that choice, right? Or if I run an experiment, I get some data. Do I have evidence, more evidence pointing this direction or that direction? That's kind of what hypothesis testing deals with. Okay, populations versus samples. Again, we discussed this a little bit already. So population consists of all subjects that are being studied, and a sample is a group selected from the population. Again, how can you tell what your population is? Well, you would kind of ask, okay, what statement would I really like to make? So if we're talking about heights of people in Pittsburgh, I'd really like to say something like the average height of people in Pittsburgh is 5'8". Maybe if I was a researcher, that's the statement I would like to make. Well, then my population is all the people in Pittsburgh. That might be a little bit amorphous. Again, do we mean like downtown Pittsburgh? Do we mean like city of Pittsburgh proper? Do we mean greater Pittsburgh area? Do we mean everybody who's like in that boundary that we pick like right now at this minute? Do we mean everybody who lives here? Like if people commute in for work and then leave, do they count? So if we really were going to run an experiment like this, we'd have to really get into some of those nuances and say exactly who we're talking about But for the purposes of this course, this is not a course on experimental design. So for the purpose of this course, we're going to kind of leave some of that nuance off to the side. And we'll say, if we say something like, I want to say the average height of people in Pittsburgh is 5'8", we'll say the population will be people in Pittsburgh, like all the people in Pittsburgh, and we'll just kind of leave it at that level. And again, a sample, it's a group selected from the population, typically selected at random. So we kind of think of, if we numbered each person in the population and we went to Excel and said, give me 1,000 random numbers, and we took all the people that are associated with those numbers and we measured their heights, that's a sample. Why would we ever work with a sample when we want to know about the population? Well, because typically we can't know everything about the population. We're not going to get 100% cooperation, and we usually don't have the time, the energy, the money, the resources to study the entire population. Or sometimes the experiments are risky, right? In terms of, say, a clinical trial. Sometimes there are time issues, right? The people who have a disease right now, if we want to know how to treat it, people might develop that disease in a year or 2 years. We obviously can't test those people right now. They don't have it yet. So in statistics, usually we want to say something about a population, but we're kind of stuck dealing with samples and making statements about samples. And that's where that inferential statistics side of things comes in, where we want to develop things. We want to develop our experiments. We want to make our statements in such a way that the statement that we make about the sample is informative about the population. And we have names for statistics for samples and parameters for population. So if we have, let's say, an average, I could talk about the average height of people in Pittsburgh. If I was talking about the population, all people in Pittsburgh, I would say that that's a parameter. That's the population average or population mean. Where if I was discussing the sample, say I took a sample of size 100 of people from Pittsburgh and actually measured their heights, got my data set, crunched the numbers and got an average from there, that would be a sample average. I would call that a statistic. So statistics, we typically deal with statistics that are estimates of parameters. So I hope that when I compute my sample average with a well-chosen sample of a proper size, when I compute my, say, sample average, that statistic, I hope that that number is going to be pretty close to the population parameter, the population average. And I mean, right now I say we hope, but chapters 7 and 8, we're going to develop the mathematics to say, how confident will we be that it's, so close to that our sample, say, mean is so close to the population mean. So we're definitely going to dial that in later on in the course. It's not just like we just say, oh, I hope it's good, and kind of we're done with it, right? So a couple examples here. This first example is clearly talking about the sample. Of the people sampled, 12% of them were found to be diabetic. That is definitely a statement about the folks in the sample. We would say that this is a descriptive statistic. Versus a statement like this, based on a study involving 1,300 people, we estimate that 12% of Americans are diabetic. Clearly, 1,300 or so people is not all of Americans. We're saying based on a sample, our sample proportion was 12%. We're extrapolating that and saying, okay, based on this sample of 1,300 people, we think that that ratio is going to stay consistent when we expand our view to all of Americans. And again, that might be a good or a bad thing to do, right? If we went to a preschool or something, and if that was our sample, if we went to a bunch of preschools, that's probably not going to generalize to all of Americans very well. Or if we went to a nursing home, it's not going to either. If we went to a hospital, that's not going to generalize to all of Americans very well either. So how we take our samples is quite important. The size of the sample is also important. If I took a sample of size, 5, and I wanted to generalize to, a population of all of Americans, that's probably not going to be a large enough sample for me to have kind of representation of all of the different, facets of Americans. Okay, so Moving on to the next topic, variables and types of data. So for variables, we can split all variables into kind of two types. One is qualitative, and the other is quantitative. So related to the words like quality versus quantity. Quantity being like how much or how many, quality being like a more general characteristic. Qualitative variables are variables that can be placed into distinct categories, where quantitative are numerical and have a natural ordering or ranking. So for instance, a quantitative variable might be something like number of students in a class, where qualitative might be something like shirt color. And not color as in like wavelength of light, but something like, red, blue, green, that kind of a thing. Can anybody else think of an example of a variable and whether it should go under qualitative or quantitative? And let me pop chat back up. You can type in chat or you can speak up. So any thoughts on an example of a variable and whether it should go under qualitative or quantitative? Yeah, number of books in a bookstore. Types of jersey a team has. Yeah, like home jerseys, away jerseys, like retro or something like that. I think that's what you were kind of getting at with that. So number of books in a bookstore would be quantitative, and then type of jersey would be qualitative. These are distinct categories. You're like either the home jersey or the away jersey. You can't be like in between. Any other thoughts on variable and whether it's qualitative or quantitative? Yeah, like number of, say, like, number of Cheerios or something in like a box of Cheerios. In a box. Or if we had, say, like cereal brand, whether it's like, Cheerios or Frosted Flakes or mini wheats or something, that would be qualitative, right? Those are distinct categories. There's really no natural ordering or ranking. Now, something to note is in qualitative, we can impose an ordering or ranking. We could list the cereal brands and then rank them by alphabetical order or something. But that ranking is really disjoint from anything meaningful with the cereal brands, at least in the vast majority of cases, right? If you put Cheerios third or something like that, that doesn't really tell you, that Cheerios is better than Frosted Flakes or something like that, or right? Yeah, different majors offered by a college, that would be qualitative. So if you're an accounting major, a business major, a nursing major, those could all be shuffled around and there's not a natural ranking or ordering to them. Pass versus fail, not percentage. That could be a bit of a tricky one, whether that's qualitative or quantitative, because there is kind of a natural ordering there. So I think I would probably put that under quantitative, as well as, say, like course grade as a percentage, 80, 90% or something like that. I think, pass versus fail, like passing is like fundamentally like better or something like that than failing, or those, I think there is a natural ordering there. Yeah, so NFL teams in the playoffs would be qualitative. If we're talking about, say, something like team names, but if we were talking about, say, you know, um, let's say like points per game, that would be quantitative. Oh yeah, okay, so like NFL rankings. Uh, and just for ease of understanding, let's just suppose that we went across the whole NFL and ranked all the teams, like this is the best team, second best, third best, and so on. I know they don't exactly work that way. There's divisions and they rank them within divisions and all that, but let's just pretend that we ranked all of the teams first to last. Yeah, so like an NFL ranking, which team is in first place, second place, third place, and so on. That would be quantitative. Yep, there's a natural order there. Yeah, different flower types. That would be qualitative. Some other things that are quantitative are things like maybe height or weight. So a lot of these like physical measurements are going to be quantitative. Things like vitals for, our nursing and medical folks. So things like blood pressure or heart rate, your sodium level, potassium level, glucose level, all of those kind of things. Yeah, age would be quantitative. So like how old are you? What are a couple other examples? So what about something like zip code? Do you think the zip code would fit better in qualitative or quantitative? Yeah, zip code is, it's a bit strange because it's really qualitative, right? It's really just kind of a numerical representation of a place name, a geographic location. It is a little bit quantitative in that like the ones tend to be on the East Coast and the nines on the West Coast, and they kind of, go that direction. So zip code is a little funny. It depends a little bit on, what your perspective is. If you're looking at the US as a whole, maybe the ones are on the east, nines are on the right, and it kind of goes across like that. But if you're looking in a geographic region like in Pennsylvania or in the greater Pittsburgh area, your zip codes are essentially randomly distributed geographically around. They're just essentially numeric representations of place names. So especially if we say, zip code with kind of a local perspective, this kind of points something important out. Remember, George Box's quote, all models are wrong, some models are useful. We're talking about variables here and we're trying to model them as qualitative or quantitative. Could somebody make an argument that zip code should be quantitative because, the ones are on the East Coast, the nines are on the West Coast, there's a gradient there, like there is some kind of natural ordering, perhaps, It also sometimes depends on exactly what question you're asking about a variable. If you're saying, if I wear this shirt color versus that shirt color, will that make me physically warmer? Will it absorb more light or reflect more light? Well, that's really a physics question, right? And that really has to do with like wavelengths of light that it's absorbing or reflecting. And maybe then all of a sudden, shirt color does actually become quantitative because we're thinking of color in terms of wavelengths of light rather than just like, is it red or blue or green, and which one do I like to wear or something like that, right? So there is certainly nuance here, but we're talking more in general terms, things that questions we would typically ask about these variables. Exactly, yeah. Occupations would be occupations. The first three numbers of a person's phone number. Yeah, so yeah, zip code or area code. Yep, that's pretty similar to zip code, exactly. Yeah, so things like wage or salary, quantitative, yep. Music types. We could say something like maybe temperature. I think that's probably good for now. Let me just make sure that I got all of the ones that I want to kind of talk about. Okay, I think that's oh, let's do number of stars. Sorry, got a bit messy. Stars on an Amazon product, right? Is it like, 3-star product? Is it a 5-star product? Do people tend to like it or not? So these ranking systems, they're what, ranking systems and recommender systems. And so what is the ranking or rating system? Okay. I feel like there's a different name for ranking system. I don't think it's called a ranking system. I can't think of the name right now. Yeah, so this was a really good list of variables. I minimized chat, so if you're still, so don't worry about bringing forward any more variables. I think we have a pretty good assortment here to work with. So qualitative variables are kind of, I think we're kind of good with that. Quantitative variables, though, we can kind of split quantitative into two different subtypes: discrete versus continuous. So a qualitative variable is just a qualitative variable. That's what it is. But a quantitative variable could be discrete quantitative, or it could be continuous quantitative. Now be really careful about the definitions here. Discrete variables assume only values that can be counted, where continuous variables can assume an infinite number of values between any two specific values. Or another way of thinking of continuous variables is that we have to round them in order to either measure them or to write them down or to communicate them in any way. Something that we're not talking about here. A lot of people see the word continuous and they think temporally. They think in terms of time. They think like, oh, are we like continuing to collect data over time, or are we like collecting data and then stopping? That's not what these mean. So this is talking about the types of measurements that we perform on these data. So for instance, something like number of students in a class, this is going to be discrete quantitative, because I can have 1 student or 2 students or 3 students, but I can't have a number of students between 1 and 2 students. I can't have 1.5 students or 1 3/4 students. If I have 8 students sitting in a classroom, if I look really hard or if I measure really accurately, I still have 8 students. I don't have 8.1 students. If I, measure more accurately, it's just 8 students. But something like, say, height, say a person's height, that's going to be continuous, right? I might measure somebody's height really quickly and, not very carefully. And I might say, oh, they're about 6 feet tall. Well, if you measured more accurately, could you get more decimal places of accuracy? Well, sure, maybe they're like 5'11.5" about. Well, if I measured even more accurately with a more careful, process with a better device, could I get to 5'11.45, 5 feet and 11.45 inches? Sure, I could keep adding decimal places to my representation of that person's height if I measure more accurately, more precisely. If at some point I actually have to define what I mean by a person's height more precisely, if I'm down to a millionth of an inch or something, like does the hair count or not, I don't know. But if I measure more accurately, if I put in more time and effort, I can add more decimal places to the representation of my a person's height. I don't care how accurately you measure 8 students in a class, it's just going to be 8. It's never going to be 8.1 or 7.9 students in a class, even if you look really hard or use a fancy measuring device. So what about something like points per game, discrete or continuous? I'll pull up chat again so you can pop it in the chat. Points per game in like, an NFL game or something like that, discrete or continuous? Yep, discrete. You can get 3 points, you can get 4 points. I guess in theory you can get 4 points, but you can't get 3.5 points, right? There's a limit to the accuracy. NFL rankings. You can be first place, you can be second place. Can you be 1.5 place? Well, no, that's going to be, that's going to be discrete. What about weight? Some brick or something could weigh 5 pounds, it could weigh 6 pounds, could it weigh 5.5? Sure. Could it weigh 5.25? 5.1, 5.13589. Yeah, that's going to be continuous. Blood pressure. Now we usually represent blood pressure in terms of round numbers, like 120/80 or something, but if we had a more accurate manometer, could we measure that pressure more accurately? Sure. Again, at some point we might have to actually redefine what we even mean by blood pressure, but sure, with a more accurate device, we could say it's really 120.7 over 79.8 or something. Heart rate in terms of beats per minute. This one's actually pretty difficult, right? I would really want to put it just a question mark here. I'm not really sure. What do we mean when we say beats per minute? Do we mean like literally in this minute, how many beats did it beat? That's discrete. Or do I mean I'm going to kind of sample for 1 minute and make an estimate of, on average, how many beats, per minute does your heart beat like over your lifetime? That's probably, something more like continuous. That's kind of a tough one. Something like temperature, I think we can see that would be continuous. I think we're starting to see that like physical measurements tend to be continuous. Something like age, this could kind of be either one, right? Discrete or continuous, depending on the perspective. If I say like, how many years old are you? In other words, how many full years have you lived so far? Have you had your 26th birthday yet? If you've lived 26 full years, you're 26. If you haven't lived only 25 full years, you're 25. That would be discrete. But if I said just like, what's your actual age, like the amount of time you've lived since you were born, that would be continuous. You could have lived 25.5 years or 25.138 years. Course grade, A, B, C, D, F. There's definitely a natural ordering or ranking there, but is there a grade between A and B in this structure? Well, no. I mean, maybe some schools have A- and B+, but then we could just say for those schools, okay, is there something between A and A- or between A- and B+? No, for these kind of letter grades. Oh, sorry. Course grade letter would be discrete, but course grade percentage, that probably would be continuous. I did them in the opposite order. So course grade percentage, we'd probably say that's continuous, right? Somebody could have an 89%, somebody could have a 90%. Could somebody, at least, within reason, get between 89 and 90%? Well, sure. Now, I mean, I guess like at some point you could say, well, if there's only so many points that can be awarded on exams and all of this, at some point you could really get into the nitty gritty and maybe make an argument for, say, discrete or something. But I think that would be really splitting hairs to try to argue that it's anything other than continuous. Pass versus fail, pretty clearly discrete. You either pass or you fail. Number of Cheerios in a box, you can have 1 Cheerio or 5 Cheerios. We'd have to say, like, what would happen if you get like, a broken Cheerio? Like, does that count as a quarter of a Cheerio, or does that just not count as a Cheerio because it's not a whole Cheerio? And for that matter, what counts as a whole Cheerio? If you have the whole circle, but there's a little nick taken out, is that? So again, at some point you can really start splitting hairs, but all models are wrong. Some models are continuous, or all models are wrong. Some models are useful. I think calling this continuous would probably be a bit of a stretch. I'd probably go with discrete here. But again, maybe, somebody else could, in a certain situation, they might want to count the, little chunks of Cheerios and say, oh, that's 1/7 of a Cheerio, and this one's 1/16 of a Cheerio or something. I don't know. They can count all of the dust in the bottom. Each little speck of dust is like 1,000th of a Cheerio. I don't know. At some point it gets a little absurd, right? Because just the way that we talk about things is in general a little imprecise. Like, what is a Cheerio? A speck of dust is not a Cheerio. A whole Cheerio is a Cheerio. But like, if I have 90% of a Cheerio and it has a little slice taken out of it, does that count? Like, we just are imprecise in language in general. So at some point we just run into that barrier. Number of books in a bookstore, again, likely discrete. If somebody ripped the book in half and stole the front half of the book and left the back half of the book, I don't know. But we're probably thinking discrete here, right? There's probably an inventory system and they say we have 1,000 books that are currently in the bookstore for sale. That's probably discrete. Same with something like salary, like your annual salary, you can only make so many dollars and cents. If you make $25,000 and 0 cents versus $25,000 and 1 cent, can you make between those two? No, not really. But like, do we care about something that's at the 7th significant figure? Like, if you can get 3 significant figures of accuracy in most things, when you're working in real world conditions, you're pretty happy. Do you care about 7 or something sig figs? Probably not. We might be able to make an argument either way here for salary. Okay, so I know we're just about out of time, but just to give you a little bit of a preview, when we come back, we're going to talk about measurement scales. We're going to take all of these variables and consider that maybe we've gone out and we've gathered some data for these variables. And we want to say, what would that data be? Where would we place that data in these measurement scales? Nominal, ordinal, interval, or ratio for each of these variables. So take a look ahead at those topics for next time, read through them, look at the examples, and then when we come back next time, we'll go through these same variables here and we'll label each of them as nominal, ordinal, interval, or ratio.